Hello students, today we will discuss about time domain response from pole zero plot. First of all, we will be given by a network function. So for a network function, we can draw the pole zero plot. You know that the network function will be in the form of P by A by B or P by Q form. So from the numerator and from the denominator, we can assume the zeros and poles. That means the roots of the numerator will give the zeros and from the roots of the denominator we will get the poles. So by using these zeros and poles we can draw the pole zero plot. Usually it is drawn on a graph sheet having real axis and the imaginary axis. Real axis is along the x-axis and imaginary axis is along the y-axis. So from the pole zero plot, it is possible to find out the time domain response. So there are two significance. That means from the network function we will be able to find out the poles and zeros so that we can draw the pole zero plot, and from the pole zero plot we will get the time domain response of a network function. So suppose we are having an array of poles and zeros. So we can draw a graph having real axis as denoted by sigma and imaginary axis as j omega. And here we are marking the different poles as C. Here poles are marked as crosses and zeros are marked by, usually the notation using for marking the poles and zeros are, poles are marked by using crosses and zeros will be marked by using circles. Now here it is a plot that is showing the poles of the network function alone. See, you can see here is a cross mark and here another cross mark here and here, all are poles representation. So there are S1, S2, S3, S4. Here you can see that S1 and S1 conjugate poles are there. That means both are complex conjugate poles. That means if one pole is, if one root is A plus IB, one pole is A plus IB, then the other will be A minus IB form. Similarly, you can see S2 and S4 are staying at the real axis. That means they are corresponding to real numbers. Similarly, there is another set of poles, that is S3 and S4. You can see that if S3 is in the form of A plus IB, then S3 conjugate will be in the form of A minus IB. So in this graph we can find that S1 and S3 are complex conjugate poles. Here S1 is here and S3 is here, and S2 and S4 are real poles. So if the poles are real, then the quadratic function corresponding to those poles will be like this. See, s square plus 2 delta omega ns plus omega n square for delta greater than 1. That means if this is the form of the equation, then its roots will be real. That is its meaning. That means if the poles are real, then the quadratic equation will be in this form, and in this case delta value will be greater than 1, where delta is the damping ratio and omega n is the undamped natural frequency. So if this is the quadratic equation, or in this case the poles will be real functions. So the roots will be in the form minus delta omega n plus or minus omega n into square root delta square minus 1. Here delta will be greater than 1. That means this root quantity will be positive quantity. So that means there is no imaginary term in this roots. So that is why it is saying that poles are real. So if this is the equation and in this delta is greater than 1, then the roots will be in this form. Roots means here it means that the poles will be in this form. That means the poles will be real. So for these poles we can plot the time domain response. So see, if this is the roots, then the corresponding, suppose if we are having a function which is in the S domain, then if we are taking the inverse Laplace transform, we will get the time domain response. So the time domain response will be in the form, see here it is denoted as I of t. So there is no significance of representing it in the form of I of t. You can use any notations such as u of t, S of t, R of t, any letters you can be used. So now we are considering about networks. Here we are using I of t notations, but there is it is not indicating that it is a current. So it is similar notation, or it is a variable value. So its time domain value will be equal to k2 into e raised to s2t plus k4 into e raised to s4t. See, if this is the roots, then the corresponding time domain response will be k2 into e raised to s2t plus k4 into e raised to s4t. See, s2 and s4 are the roots, real roots. If these are real roots or real poles, then the corresponding time domain representation will be like this. So this is the response. So here k2 and k4 are unknown, so you have to find out its values. Okay, so we will see how can we find out this k2 and k4 values in the next slides. Before that, here you can see that it is an exponential function. Here also it is also an exponential function. So corresponding to this term, the response will be like this. I of t will be like this due to S4. See, this is for S4. And also due to S2, the response will be like this. That means you can see from the figure that the response due to the pole S4 dies faster compared to that of the S2. See, here there is a drastic change from the higher value to lower value. But here the higher value of response I of t changes slowly and finally it decays to 0 in a slow manner. So from the graph you can see that the response due to the pole S4 dies faster compared to that of the S2. So next, now we have discussed about the poles S2 and S4 alone. See, S2 and S4 are real poles. Next we have to consider S1 and S3, which are the complex conjugate poles. So when we are considering the complex conjugate poles, then the quadratic equation corresponding to this complex conjugate poles is s square plus 2 delta omega ns plus omega n square, and in that case delta will be less than 1. See, once you are giving that poles are complex conjugate, that means there is a imaginary term, right? That is one root will be a plus ib form or a plus jb form, other will be in the form of a minus jb form. That means there will be imaginary part, or j term will be there. So in this case, so we can write this roots are s1 comma s1 conjugate. That means that will be equal to minus delta omega n plus or minus j omega n into square root 1 minus delta square for delta less than 1. That means when delta is less than 1, then we will get the roots as complex conjugate poles. That means root quantity will be a negative quantity. That is why we are getting j symbol like this. So we can write it as, if delta is less than 1, then s1 conjugate will be minus delta omega n plus or minus j omega n into square root 1 minus delta square. So in such cases, that means when the poles are complex conjugate poles, we will get the time domain response in the form I of t equal to, similar to the previous case, instead of s, s2 and s4, we have to substitute the roots s1 and s1 conjugate. That means the response will be k1 into e raised to minus delta omega n plus j omega n into square root of 1 minus delta square t, plus other root is k1 conjugate into e raised to minus delta omega n minus j omega n into square root of 1 minus delta square into t. So instead here minus delta e raised to minus delta omega n into t are common in both equations, so we can take it outside. Suppose k1 and k2 are constants, so we can represent it as k. So that will be equal to k into e raised to minus delta omega n into rest of the term will suddenly represents sine omega n into square root of 1 minus delta square into t. That is all simple mathematical procedure. So the final equation will be k into e raised to minus delta omega n into t into sine omega n into square root of 1 minus delta square into t. So if we are plotting this time domain response, you can find that the response due to the complex conjugate pole is damped sinusoid. That means there is a sine function, and that sine function will decay when time approaches infinity. So in this figure, you can see that this is the response due to S1 and this is the response due to S3. From the figure or from the graph, you can see that the response due to S3 dies faster than that due to S1. You can see it approaches to 0 certainly comparing to this due to S1. That means the response due to S3 dies down faster than that due to the S1. So this is the case of the complex conjugate pole. So next we have to find how can we solve a problem if you are giving a network function, and how can you solve for the time how will you get the time domain response from the network function. So this slide will show you how can you find out the time domain response once you are giving a network function. Here it is given that the transfer admittance y of s. See, you know that what is admittance? Admittance is current divided by voltage, right? So y of s will be I of s divided by V of s. So you want to find out the current, time domain response for the current. So from the admittance equation you can write it as a current will be equal to voltage into admittance, right? So you can write it I of s will be equal to V of s into Y of s. So this is in S domain, right? So you have to find out the time domain response. That means you want to find out I of t. So here we are dealing with the time domain response calculations from the pole zero plot. So we have to initially draw the pole zero plot, okay? So I of s will be in the form, I of s will be equal to V of s into Y of s. You know that a network function will be in the form of a rational function. That means it is in the form of P by Q form. See, here all are functions of s. So we can write it as a P of s by Q of s. So we can write I of s will be equal to, this function can be written as a, see, this is the ratio of two polynomials. So we can write it as a h into s minus sa into s minus sp etc. up to s minus sn divided by s minus s1 into s minus s2 etc. up to s minus sm. Here h is a scale factor, and also here you know that this is the numerator polynomial which correspond to p of s, and this is the denominator polynomial which correspond to q of s. Here you can see that numerator will give the zeros, right? Your zeros are SA, SB, Sn, and denominator will give you the poles. That means the poles are S1, S2 and Sm, right? That you should remember, and you have to draw the graph of pole zero plot using the zeros and poles. See, when you are drawing the pole zero plot, poles are marked by the cross symbols and zeros will be marked using the circles. So, in order to find out the I of t value, see, we have now this equation I of s in the form of P of s by Q of s, or in this form. So, in order to find it, we have to first take the inverse Laplace transform. So, for that we are taking the partial fraction expansion method. That means we can write I of s in the form of I of s will be equal to k1 by s minus s1, k2 by s minus s2 plus etc. plus km by s minus sm. See, this is a usual procedure for finding the partial fraction. So, the time domain response can be obtained by taking the inverse Laplace transform. So, I of t will be equal to L inverse of this I of s. What is I of s? I of s is this quantity. So, k1 by s minus s1 plus k2 by s minus s2 plus etc. plus km by s minus sm. So, this is the time domain response. So, we have to find out k1, k2 etc. up to km. So, we have to use this pole zero plot in order to find out this value, rather going for finding the I of t value simply by using the inverse Laplace transform method. So, any of the coefficients of the above equation can be obtained by Heaviside methods. So, Heaviside methods usually uses the pole zero plot graph. So, we are going for that method. So, to find the coefficients k1, see k1, in order to find k1, what is our regular procedure? See, we are having an f of s function, then k1 will be found out by f of s into s minus s1 at s is equal to s1. That is our procedure. Similarly, we can write k1 will be equal to, what is here I of s? I of s is this function. See, this is the I of s function. So, I of s will be multiplied by this s minus s1, and we will substitute for s is equal to s1. That is our regular procedure. So, we can write k1 will be equal to h into s minus sa into s minus sb into etc. up to s minus sn divided by s minus s1 into s minus s2 into s minus sm into s minus s1 at S is equal to S1. So that is our regular equations. See here they are using L, sorry I have said that it is S1, see this is SL, here KL, this is at S is equal to SL. So SL, SM and SN are all complex numbers. Here these all are complex numbers. So the difference SL minus SN will also be a complex number. So we can write that, see if this is a complex number, then we can write it in the form of a complex number will be equal to mln into e raised to j phi ln, right? See SL minus SN will be a complex number, and that complex number can be written in terms of its magnitude and phase. And phase component is represented as a ratio of exponential function. So m ln into e raised to j phi ln. M is the magnitude and phi is the phase angle. So here you can write it, KL will be equal to H into MLA into MLB into MLN divided by ML1 into ML2 into etc. up to MLM into e raised to j LA plus phi LB plus etc. plus phi LA, phi LN, phi LN minus phi L1 plus phi L2 etc. plus phi LM. See here what is we are doing that here there are different complex number terms. So we are representing each and every complex number terms by its magnitude and phase. That is why we are getting M. This is MLA, this is MLB, this is MLN, and at the denominator side we are getting ML1, ML2, MLM, MLM. And also we are getting the phase angle as e raised to j phi LA, phi LB, phi LN. See here this is a multiplication term, so e raised to terms can be added. That is why we are getting this term, added terms. And in the denominator side also we will be having e raised to phi terms. So when it is coming to the numerator side, so we can minus the phase angle terms. That is why we are writing this equation. So this is the usual form for finding K1 from the pole 0 graph. So we will see the details when we are doing a problem. So now this equation will be a little complex, complex one, and so it will be confusing. It will be making a little confusion for you. So don't worry, it will be clear when you are doing a problem. So next we can find similarly all coefficients K1, K2 etc. up to Km may be obtained, and in this manner also this will constitute the magnitude and phase angle. So there is another method for finding K1 and K2 from the pole 0 plot. See this is the steps that we are going to adopt when we are doing a problem. First of all we have to obtain the pole 0 plot of the given network function. Next we have to measure the distance MLA, MLB, MLN of a given pole from each of the other zeros. So this is important thing. What is MLA represents? Actually L will be a pole, and so MLA represents the distance of a pole from each of other zeros. So MLA, MLB and MLN comes at the numerator side, you can see here. So this represents the distance of a particular pole from each of the other zeros. Similarly, denominator side there is ML1, M12, ML2, M etc. MLM. So in the third step, measure the distance ML1, ML2, MLM of a given pole from each of the other poles. So denominator side contains the distance of the particular pole from the other poles. So numerator contains the distance of the pole from each of the zeros, and the denominator contains the distance of the pole from each of the other poles. And here also there is a magnitude term. So in the fourth step we have to measure the angles phi LA, phi LB etc. up to phi LN of the line joining the pole to each of the other zeros. So this term phi LA, phi LB and phi LN represents the phase angle of the line joining from each pole to each other zeros. Similarly, there is phi L1, phi L2, phi LM. So what is it representing? It is actually the phase angle of the line joining the pole from each of the other poles. So when we are getting these phase angles, we can substitute these values, magnitude and phase values in this equation, and we can find out the value of K1. Once you got the value of K1, you can substitute that value of k1 in this equation, and you can find the inverse Laplace transform, so that you will get a instantaneous time domain response, that is I of t. So then how can you get the magnitude and phase response from a pole zero plot? See, the steady state response can be obtained from the pole zero plot. Once you get the network function, you can find the steady state response from the network function as the, suppose n of j omega is a network function, and it will be in the form of m of omega into e raised to j phi of omega. See, this is m of omega, means this is the magnitude, phi of omega is the phase angle. So network function can be, we can write it as m of omega into e raised to j phi of omega, where m of omega is the amplitude and phi of omega is the phase. So this is a function in terms of omega. So if we are giving different values of omega, so corresponding values of m of omega we will get. So we can plot the graph of m of omega versus omega. Similarly, for different values of omega, we will get the phase angle. So we can also plot the phase plot. So next we will do a problem. Thank you.